one of the series we did on Thursday. We first started talking about power series was this ugly mother. I called it the Bessel function of order 0. F of x, right? I can define a function wherever that series converges. And that's one of the things that's really nice about our power series, because on the interval of convergence, well, let me go inside the interval of convergence, we know we converge absolutely. At the edges, it's kind of questionable. But inside, we know we converge absolutely. That means that each value of x uniquely defines a y value. That's a function. So let me take this same idea and apply it to another series we've already seen before. 1 plus x squared plus x cubed, and so on ad infinitum. What kind of series is that? Leo?
That'd be a power series.
Yes, but what kind of power series can I, what kind of convergence test can I use on this power series will allow me to do it fairly quickly?
Make that a P series.
The only a p series is if it's 1 over x to a power.
Geometric.
Aha, that's geometric. As a matter of fact, it's geometric with a equal to 1 and r equal to x. Okay, wait a minute. Geometric series have well-defined sums inside their interval of convergence. What's the sum and what's the interval for this one? You've seen the answer to both of those questions previously. They should be in your notes from Thursday.
On the 1 over 1 minus x.
Right, because it's a over 1 minus r. On what interval does that converge?
Which is the one's less than x.
Right, or in absolute value of r is less than 1, right? Now here is a really interesting idea. Because what I've done is I've said, hey, I've got an infinite series, and between -1 and 1, I know its exact value automatically. That's a series representation of a function. Now, ready for the $64,000 question? Why should I give a flying this function is defined everywhere except x equals 1. Between -1 and 1, I can use this instead. Which means instead of dealing with division, I can deal nothing but a polynomial. As long as I know how many terms I need to get the error as small as I want, and we know how to figure out error. Son of a bitch. Do me a favor, grab your graphing calculator. I want you to graph two things for me. I want you to graph 1 over 1 minus x. And then I want you to graph a bunch of polynomials. And I want you to do me a favor, and I want you to set the window to be fairly small. How about that for a window? So when I do this, and I graph this function, I get this picture. And that's got a vertical asymptote of 1. If I add in the line y equals 1 plus x, wait a second. That line happens to be the tangent line at 0. I've seen that before. Chapter 3, section 11, linear approximations. I used a line and I said, hey, you know, close to 0, that line and that curve aren't that far apart. If I add in the quadratic term, it's even closer, isn't it? So here is the original equation. There's the straight line. There's the parabola. And it goes really close. Matter of fact, if I add the cubic term, it's even closer. This sequence of functions now creates a better approximation, not just a linear approximation, a quadratic approximation, a cubic approximation. How close do you want to get? I claim that I can do this same trick using this idea for any function that resembles a geometric one. As long as I can figure out how to take my function and turn it into something that looks like a over 1 minus r, I can make this work. And I can turn my function into a power series. Questions? Yeah.
Like my graph, what modes?
I'm sorry?
What modes? Yeah, my graph.
Yes, but I zoomed in quite a bit so that I wouldn't have to see anything outside of the interval from -1 to 1 in x, because that's where my radius of convergence is. Outside that interval, my series diverges. So I don't want to look there. I don't want to look in the interval of convergence for my power series. And yes, if I were to go back to the standard window, I would see that the original function has that vertical asymptote. And to the right of my vertical asymptote, my functions aren't anywhere close to 1 over 1 minus x, are they? Because the series diverges out at that point, diverges to infinity. So I really only need to look in my interval of convergence. Make sense? Okay. So the real question is, how do I do this? Because once I see that form, I can jump right to a geometric series. And the answer is, it depends on f of x. And we're going to do a bunch of algebra. My problem here is in the denominator. I see number over 1 plus x squared. What algebra trick could I do? I can't separate denominators. I can only separate numerators in a fraction. Leo? I hope not. Because as x goes to infinity, that limit is 0, and I'm not sure that helps me at this point. Taking a limit and knowing that that limit is 0 tells me I'm not going to get something that diverges. But remember, my goal is to make it look like this, a over 1 minus r. So it's really the sign in the denominator that's my problem. This is 1 plus, and I want it to be 1 minus. We did this for ellipses and hyperbolas and circles and parabolas, where we changed addition to subtraction to find h and k. What did we do? That was only a chapter ago, people. Chapter 10, section 5. Yeah?
1 minus the negative x squared.
Ha! Addition, double negative, yeah, those match up, right? Well, hey, wait a minute, that's a over 1 minus r, but the r is negative. It's okay. So now I can say, wait a minute, that means I can jump directly to this power series, and I can say, oh, that's a geometric series, and goes from 0 to infinity, a r to the n. 99.999% of the time in this section, it will be to my benefit to use AR to the n rather than AR to the n minus 1, starting with n equals 0. I said this on Thursday about negatives inside the n power, that I've found it most often helpful to split those up. So I'm going to do that here. And I'm going to rewrite this as minus 1 to the n, and then x squared to the n. What do I do with those two powers? And so I get x to the 2n. I have a power series. What's the radius of convergence? Advantage. You know the answer to that. It's right above this example. Because this is a geometric series, it only converges inside r less than 1. So I take the absolute value, and I make that less than 1. I could do the ratio test, but then I'd have to check the ends. But since I was starting with a geometric series, I don't have to. Questions? As always, the sneaky part of this is now I got to do the algebra up front to make things look right. And sometimes that algebra is obvious, sometimes it isn't. Okay, the first thing that makes me twitchy is the fact the denominator is not 1 minus something. That's plus 2. My goal is to make it a over 1 minus r. If I know I need to make it 1 minus, I'm going to go ahead and rearrange. Now the number's in front, which is at least consistent with my other goal, 1 minus something. But it's a plus. So let's play the same trick we just played. Well, now what you going to do? Divide everything by 2. If I divide on top by 2, that makes the top a 1/2. Makes the bottom 1 minus negative x over 2. Just like with our polar conic sections, where we needed to make it 1 plus or 1 minus in the denominator to get the eccentricity. Son of a bitch, the stuff I'm doing is the same stuff. That is a over 1 minus r. What is the corresponding geometric series? Exactly. Now, 99.9% of the time, that's good enough, walk away. I'm going to fuss with this a little because of that minus sign. I want to pull that out. Then I have a fraction inside that power also, right? So let's separate that, put the n power on top and the n power on the bottom. So I get minus 1 to the n, x to the n, and a 2 to the n. But wait, there's also a 1/2 in front of this expression, isn't there? So there's one more 2 on the bottom. Gesundheit. And by combining all the 2's, I get a 2 to the n plus first power in the bottom. Why would I do this as opposed to the other version? Because now I clearly see the power of x, and I see the coefficient that goes with it, Cn x to the n. That's my power series, isn't it? Cn x to the n. And some textbooks will actually write it that way. Taking the x to the n to the outside. Questions? I'm going to make this problem much more difficult. This particular series is only different from the previous one with that extra x cubed on the top, right? Which means I would go through all of the same algebra here. What would I end up with on top at this end? Say again? But I also need to take care of that x cubed, don't I? So what would end up on top there is x cubed over 2. And really, if I think of taking the x cubed out front, doing all the same algebra we see at the top, and then putting the x cubed back in, I end up with exactly this expression, which makes my power series have x cubed over 2 here. I have a different a. Now here's why I took stuff apart. Because I don't like having 2 different places where x is in this series. I really only want 1 power of x. But by doing this algebra, I know what happens to this part when I separate those pieces. And this time when I combine stuff, I can combine the x powers as well, making this minus 1 to the n over 2 to the n plus 1 with what power of x? Multiplying things with the same base, I add the powers. And now, I was about to ask you what changed in the radius of convergence when I looked back and realized we didn't do the radius of convergence in the previous one. Oops, that was a mistake. Let's go back and do the radius of convergence up there. So let me back up a little. What's the radius of convergence here? In a geometric series, there's strict inequalities because it's r and absolute value is less than 1. But in this case, r is not x. In this case, this is r. And the absolute value gets rid of the minus sign in there. So I have x over 2 is less than 1, which means in absolute value. So I get absolute value of x is less than 2, which really means this one goes from -2 to 2. The radius of convergence here is 2, not 1. Now I can ask the same question down here. What's the radius of convergence this time? Why? R is still exactly the same. This has exactly the same radius of convergence. So here's an interesting idea. The only difference between these two functions was that extra x to the third out top, right? So I can multiply by x's. I can multiply by numbers. I can do these adjustments within functions, and that means I can do them within series as well. So another way to do this same problem is to say, I am looking at f of x equals x cubed over x plus 2, which is the same as x cubed times 1 over x plus 2, but we know that power series. And that's the power series we got 2 problems ago. Right there. I just copied it over. And then what I'm really doing is I'm saying, oh, I want to multiply the x cubed. I want to distribute, because that capital sigma is add all this crap up. So by the distributive rule, I could multiply the x in each and every one of those terms, and that would increase the power by 3 on each of them. So I just multiply it in here. So here's something really different about derivatives and integrals versus series. I could not move x's across an integral symbol. I could not move x's across a derivative, but I can move an x across the sum. Because it's really just a set of parentheses. Problem is what's inside the set of parentheses is infinitely long. That's weird. I told you last time, infinity's weird, man. Now, if I hadn't done this problem already, I would still have to do it with the geometric technique we just learned, but having already done it, I have it in my hand. Let's use it. Questions? All right, so let me go back to the very first function, other than the Bessel, because the Bessel was atrocious. We said this power series was the same as that function inside the interval from -1 to 1. And it's absolutely convergent there. But on the left, I have a function. This is the calculus class. Let's do some calculus. What's the derivative of 1 over 1 minus x?
Both of them are running y, that's to the top, y at the top, and that's to the bottom, and the bottom squared.
Absolutely correct. However, because that top is a 1, its derivative is
0.
Which means I could use the chain rule for this, right? Right, that is 1 minus x to the -1 power. Either way, what do I end up with? You can do the derivative however you like. What? Okay, so if I do that, then I get -1, 1 minus x to the -2, but wait, there's more. Chain rule. Ha, those -1s are going to cancel. That's 1 over 1 minus x quantity squared. Now, I am 100% sure that this is not geometric looking. It's not a over 1 minus r. Because that entire denominator is squared. That is going to be a major pain in the ass to rewrite to try and make it look geometric. So I don't want to do that. But it's the derivative of this, which already has a series. Ignore the fact that I wrote it like this. Think of it as a polynomial. Do you know how to take the derivative of that thing? Derivative of 1. Derivative of x squared. I know how to do these. I've been doing these for a year. Wait a second. Wait just one frickin' second. All I'm really doing is the power rule, right? Derivative power of x is put the power out front and subtract 1 to get the new power. So what if I just did that in this notation? the derivative of a series. Wait a minute. This is just adding a bunch of stuff together. And if I take the derivative of a bunch of stuff added together, take the derivative of each one at a time. Which is nx to the n minus 1. So the first one is 0x to the whatever, then 1x to the 0, then 2x to the first, 3x squared, son of a, that's exactly it. And if that's the derivative of this version of f, then that's the derivative over here. That means this has a power series. Both of those are f prime. Those must be equal to one another. But only in that same interval of convergence. It only works where this series converges. Holy crap. I had something I could not take the geometric idea directly, but I could take it indirectly. This works in general. The power series of the derivatives is the derivative of the power series. We call it term by term differentiating. All I did was, instead of doing the derivative of the whole thing, I did the derivative of each piece. Constant stayed there. Derivative of stuff to the n is n stuff to the n minus 1 times the derivative of the inside. Derivative of the inside is 1. So really, I took the derivative from the outside and put it on the inside. This is a hugely powerful idea and took several different mathematicians about 50 years to show why it would work inside a given interval of convergence. This is one of the deeper, more meaningful, important proofs in calculus in general, in the field of analysis. It's important, but we're not going to look at the proof. We're just going to accept it on face value. Yes, ma'am. That's x minus a to the n. Because all I did was take this exact term and put it in here. Questions? If I can do it for derivatives, do it for integrals too. The integral is on the outside. No, it isn't. Move it inside. Still works. The integral of a whole bunch of crap added together is the integral of each piece added up. Okay, wait a second. You know how to do that integral.
If u 1 minus x and d would be 1 and x and a du or x d.
Now here's a question that up until a moment ago I had no idea how to answer. I would like a power series ln of 1 minus x. You'll often see this called a power series expansion rather than just a power series representation. Those two terms are equivalent here. I want to know what power series gives me that function. And my reaction is I haven't the foggiest effing idea. But I know that this function is the antiderivative here. And that's the integral of a power series. And if that's the integral of a power series, I can do with that theorem that just rolled off the top of the screen. I can switch the series and the integral. I forgot to write my dx on the top line. Got to put my dx in there. What's the integral of x to the n? And then way at the end, I should get a plus c, right? Now, in order for me not to make myself crazy, I tend to put that c in front. So rather than write it here, I'm going to write it like this. Because then you can't tell whether it's part of this piece or it's being added to the whole thing. So you could put a big set of parentheses around this, but I think it's easier to just put the c in front. I have one more problem. What's the value of c? It doesn't say, does it? But this power series should match this function. Somebody give me a value for x that's in my interval of convergence. Wait a second. What's my interval of convergence for this thing? My interval of convergence, I can't use 2. I could use, can't use 1, that's not in there. Let me use something easy. Let's use 0. Minus ln of 1 minus 0 needs to be equal to c plus 0 to the n plus 1 over n plus 1. What's 0 raised to any power? So this whole thing is 0. What's this side? Because it's ln of 1, and ln of 1 is 0. Yay, I know what the value of c is. As a matter of fact, this allows me to find series representations for functions that I would otherwise have no idea how to find a power series for. Okay, what is the derivative of the inverse tangent? This is why you have a formula sheet. Without the square root. The square root goes with sine. Hey, wait a second. 1 over 1 plus x squared. Didn't we do a power series for that? Right at the beginning of class, we did a power series for that. I have that one. I have that one right here. That means that I know that I have a power series representation for the derivative. Which means I can find a power series representation for the arctangent. Now, we didn't know how to do that integral directly. We had a lot of problems doing that integral, and it was only using the inverse derivatives that we were able to figure out that that was the integral that gave me the arctangent. But now I can say, hey, wait a minute, that's the integral of this. So if I do this term by term, the integral of x to the 2n is the antiderivative of x to the 2n.
It's the 2n plus 1 over 2n plus 1.
That's a power series for the arctangent. You ready for a better statement? I have no idea how to do that integral. None. I can't do partial fractions. X to the 4th plus 1 doesn't factor over the real numbers. If you really want to play with complex numbers, we could do that. Hell no. But I can turn that into a power series, a over 1 minus r. 1 over 1 plus x to the 4th is 1 over 1 minus negative x to the 4th. That's the power series, negative 1 to the n, x to the 4n. So don't do the integral as 1 over 1 plus x to the 4th. Do the integral in a power series. And that is a directly computable integral. X to the 4n plus 1, 4n plus 1. Let's see. Now the problem is, I don't know if this has a nice function. I sure as hell know what the series representation of that function is. That makes really complicated integrals easier to do. Matter of fact, I only ever need the power rule as long as I can write my function as a series. $64,000 question. What happens if I can't? That one's not geometric. That's not going to help. I need a new trick. That is what we will discuss on Wednesday. Have a wonderful rest of your day, everyone. I will see you all soon.